Okay. So you guys ready? Okay, so let's get started. Okay, so
It's not good.
for this first question right here, it says determine the following. This is all kind of like decimal stuff, right? Things we had like lecture 1 and 2. So on the first one, it says, what is the gain, the voltage gain, V out or V in, that equals 1,000? What is that in decibels? So on that one, so you have V out over V in, and that's 1,000. To convert that to decibels, what we do is just say 20 log 1,000. Now we're in units of decibels, okay? And then what we can do, we can simplify it by, since this log is on base 10, or there's really like a little 10 there, right? We can say this. And then anything that's like 10 raised to the power, this part right here is just 3. So it's 20 times 3 in decibels. So that's just 60 decibels. Okay? So that's number 1. Any questions about this? Okay, number 2, or B. If the current gain is, I think that's my cursor, is 140 decibels, then what is the ratio I out over I in? So for that one, we're given the decibels first. And so there, we can start working backwards, right? So 140 decibels, that's going to be 20 times 7 in decibels, right? And so that's going to be 20 log 10 to the 7th in decibels. And then just to, it's just this argument right here, 10 to the 7 is going to be this I out over I in, right there. Or you could just call that 10 million. Okay. What about that? Cool. All right, C. If the maximum voltage gain of a low-pass filter is 60 decibels, then what amount of decibels is the cutoff frequency? Okay, so that's the max right there. And so we know from that, like how many decibels down is that? Yeah, it's going to be 3. Okay, so it's going to be 60 decibels. And for cutoff, we're at a minus 3 decibels. And so that's just going to be 57 decibels. And that's going to be the decibel level at cutoff frequency. That, and then if you go lower than that, then of course that's beyond cutoff. But at cutoff, that's what it's going to be. This last one right here. Just to remind you guys, remember what that looks like when you're on the semi-log plot, where here's like 60 decibels, and if we do like a low pass, it goes like this, and then we've been doing it this way, where it's like a very sharp inflection at negative 20 decibels per decade, but it's really a curve, right? And at this point right here, that point right there where it crosses that curve, that is 57 decibels. Okay, for voltage or current. Okay, at whatever frequency this is, the cutoff frequency, right? And so, and that of course means 3 decibels. That's square root of 2 of the value. Yeah. Yeah. Yeah, that is right.
Then would that make the answer this 154?
No. This is for cutoff for the voltage, but yes, yeah. So what he's talking about, if you have a signal that's voltage or current, and you want to get half the value, then it would be 6 decibels lower. Yeah, that's like getting to power. Yeah.
So cutoff is 3 dB, regardless of where you're working
Well, okay, yeah. So yeah. Let me clarify. It's 3 decibels down for cutoff, period. But what it means to voltage, what it means to current, and what it means to power, that's a little different. Yeah, if it's for voltage and current, you've attenuated your signal by 1 over square root of 2. But if it's power, 3 decibels down, you've attenuated it 1/2. So it's like half the power. Yeah. You guys get that? Okay, so that's why that's there. And this right here, this is square root of 2 log 20. So like if you plug that into your calculator, you get 3 decibels. It's going to be close to, it's not exactly 3 decibels, but you're rounding, okay? So they just call it 3 decibels, but it's 3 point something. Okay, so this one, if the maximum power gain of a low-pass filter is 60 decibels, then then at what amount of decibels is the, I think it's the same thing, cutoff frequency. Yeah, cutoff frequency. So for this right here, for power, you're starting off at 60 decibels of power. You're minusing 3 decibels. That's going to be 57 decibels of power. But remember, if you're in power, in the power regime, this is not square root of 2. That's 2, not square root of 2. and let me show you why. So let's do it like this. If you have, what's a good way to show you guys this? Okay, so we know this, right? Let me erase that. Okay, so we know this is 3 right here, but when you're in terms of power, this is 10. So if that's 10, it's really 10 times 2 log of that. And we want to put this, we could throw that into there, so that's 10 log, why do you keep writing 3? 2 squared. And then so we have log 2, okay? And you're minusing it. If you're in the regime of decibels and you're minusing, you're really like, this is like dividing, so you're like dividing by 2, right? So things that multiply get added in decibels, and like in logs, things that are multiplied get added, and things that are divided by things are subtracted, okay? But as you can see, this is the equivalence. Like I started off in, with this 20 log of square root of 2, but every single step is equivalent to the one above it. So they really mean the same thing. I haven't changed anything, but it just means like, in that type of regime, it corresponds to a factor of 2 lower for that cutoff frequency. Okay, so still this frequency, right? But if we're dealing with power, that 3 decibels down, you're 1/2 the power. Okay. If an input voltage of VI equals 2 to the raised to the power of -3/2 volts goes into a 9 decibel amplifier, then what is the output voltage? V out. Okay. Can you guys see this board okay? Like when I... Really? Is the board coming out okay in there? Like the contrast? Okay. Should I write bigger, or is it just contrast? It's just like, I need like a thicker marker. Okay, so if the input, okay, so here's what we know. V out over V in is 9 decibels, right? And so we're trying to find out what the V out is. Okay, so 9 decibels. One way to think about this, as we've just seen, is like think about it in terms of threes, and that works out really nicely here, right? So it's really like 3 plus 3 plus 3. If you want to think about it like that, and decibels, which is really like, I mean, if you want to put it in terms of log, you can do that too. Either way is fine. But what this really means is that when you're doing stuff like this, things are being added, really being multiplied if you're not in decibels. So if you put this in terms of the regular numbers, it's going to be square root of 2 cubed, because you're really multiplying all those together, right? And your VI is what? 2 negative 3 halves, right? And so I guess you could put this in terms of power. Yeah, like that. You see that? So you can use your calculator too if you want. But basically, the way the problem is set up, you can see something is divisible by 3. And that's a good way to think about things. Like if you see a number in decibels, see if it's divisible by 3, and then, or better yet, see if it's divisible by 6. And then you'll see like how many halves it is, below or above the value that goes into it, right? So you guys okay with that? Okay, good. Okay, number 2. What are the gain, current gain, and power gain required of the amplifier if Vs is 4 millivolts right here, and the desired output power is 36 watts? So we're given Vs and we're given the desired power, and we're supposed to find all the gains, like voltage gain, current gain, and power gain. So if it's the voltage gain of the amplifier, then it's V out of the amplifier right here over Vn of the amplifier. Not this one. This is of the amplifier. This is like, some other like power source, and that power source has some resistance, and they're just grouping it together like that, or something else coming in. This could be the voltage signal of an electromagnetic wave coming into an antenna, and that's the resistance of the antenna, anything. But of the amplifier itself, that's the voltage that's seen at the amplifier for input, and that's the output voltage right there. And of course, that voltage is affected by the resistance. But anyway, so for this system right here, for the voltage gain, so is V out over V in. And so let's first find out what V out is. Wait, are we given? Oh yeah, we're given all the values of resistances. Okay, so for power, we know that it's V out squared over RL. And so we know power, right? We know power, we know RL, so we can easily solve for V out, and that's just going to be power multiplied by R squared, by RL, and take the square root of that. Okay, so this is going to be our V out. For V in, we could do voltage division, right? So what's seen right here is 50 kiloohms. So if you think about it, it's like, you know, some current source, it goes down some voltage, and then goes down some voltage due to some resistance right here that's seen right here, and this loops back around. So we can say that Vn equals Rn divided by Rn plus Rs multiplied by Vs. And we know all of these values. So we got that. So it's a ratio between those two things. And that's going to be your first thing is your voltage gain. And you just plug in your numbers. For current, so current out, that's going to be very similar to this right here, where it's power equals the current squared times RL, right? So it's going to be your power times RL. Oh wait, divided by RL, sorry. So that's the first thing right there. And so we know power, that's given to us. We know RL, that's given to us. So IN, that's going to be, well, I guess there's a couple of ways of doing it, right? We now know this voltage right here, so we could just use Ohm's law and find this current from this current. So it's going to be this voltage minus that voltage divided by that resistance. Or we could do it this way, this voltage minus that voltage over that resistance. Or we could use this, this source right here and say it's this voltage over these two in series. They're all going to get the same thing, right? So we could just say Vs divided by Rs plus Rn, if you want to choose one of them. And that'll give us this. And so now we have that ratio, I out over Rn. Now for power, the ratio of power is P out over P in. Each one of those, well, we saw these other things, but they're also like this too. So this P out right here is V out times I out, and this P in is V in and I in. And actually, we found out these separately already, right? Here and here. So we just multiply them together, and that's our, yeah.
Why is the I out over RL?
Oh, square root. Thank you. Yep. Thank you. Yeah, because I squared equals that. Yeah. Yes.
Do you want them in terms of the ratio or in terms of decibels?
Yeah, this one didn't say, huh? Well, okay, so if it said put in terms of decibels, but that's like an extra step. So if it doesn't say that, just leave it as is, as a ratio. Yeah.
So if you're given AC input, all your powers would be adjusted by, because it'd be I and V RMS for your powers, right?
Yeah, RMS for yeah, sinusoid. I mean, yeah.
So like
Sinusoid.
everything, all power would be increased by a factor of 2.
If it's a sinusoid, yeah, because you're squaring those things, yeah. But using RMS. But of course, if it was like square wave, it wouldn't be a factor 2. But you'd have to like do your calculation to figure out what it is. Yeah. That's right though. Anything else? Okay, moving right along. Number 3. Oh, great. Okay, so if your Vn is this right here, so you have this DC offset, and then it's oscillating about that DC. So this is your input. Then what does V out look like given the following voltage transfer characteristic? So it looks sort of like that. Let me try to get it on my screen. Okay. I wonder if I should lift this up and suck a right on it. I'll just right over here. Okay, so in this case right here, it looks sort of like this, and I'll try to get the numbers right, but you know it's going to be kind of difficult. Okay, but I get a few of them. Yeah, if you have 9 on top, -6 on the bottom. So this is -6. That's 9. Okay, so that one right there, that's this is your input, right? Here's your output. And so your input's coming in at 3, so 0, 1, 2, 3. So it's right here, and it has an amplitude of plus or minus 3. So it's going to go up 3 and down 3. So it's going to take that kind of form right there. So that's at 3. So let's say it's something like this right here. So let's say that's 3. Oh, that's not even close, huh? Okay, so it's going to look something like this, where it's going to go this high, that direction, that high, that direction. So it's going to oscillate like that all the way up, right? And then what's going to happen is that, so that's at 3, 1, 2, 3, so it's going to be right here. You can clearly see that that's going to be some clipping. This center one is going to go straight through like that. And this one's going to come up to like around here and then go over. So the bottom's not going to be clipped, but the top's going to be clipped. So it'll look something like this as it comes out, where it's clipped, clipped, sort of like that. So if I were to draw it out, your voltage will equal something like this. Oh, wait, let's see how. So here's 1, 2, 3. So it's going to be right here. It's going to be centered at 7, right? It's going to go up as high as 9, and that's it. But it's going to come as low as right here. So that looks like 1, 2, 2.5, like something down here. So if that's 1, 2, 3, wait a minute. 1, 2, 3, 4, 4.5. So it looks something like this. So 7 plus 4.5 cosine, what frequency do we have? 120? 120 pi. Oh, and it's going to be off by phase, right? It might be, right? Because we talked about this little lag, because everything inside of an op amp, it has like RC. So it's going to be a little bit of phase. So let's throw that in there. Or it's going to be 9. So it's this for voltage less than 9 volts, or it's 9 whenever voltage is greater than 9 volts, because it's clipped. Yeah. Okay, any questions about this? Yes. Oh, because it comes in at 3. That's just that center term. So it's coming in at 3, right? That's the input. But when it goes to the output, it's coming out at 7. See right here.
Can you explain the 4.5?
Oh, because that 4.5 part is like I looked at the it's sort of like the 3 to 7, but I'm looking at the amplitude here. So it's 3, but it's going to go over 3. You can see that 3 in front of the cosine. So 1, 2, 3. That's the amplitude back and forth. This one, no, this one's going to get clipped, right? But this one does not get clipped. You're going over 3. It goes up here to this point, and this point right here, if you go from like this 7, that's 1, 2, 3, 4, 4.5. I may be off. It might be 4.4. But that's good enough. Anything else? Okay, good. Come on. I don't think there's anything there. Yeah. Okay. So what is the gain of the amplifier in terms of resistors only? So the gain, it's the output over input. So here, if it doesn't say it, go ahead and assume it's ideal. Okay? So that's what we'll do. And if it's ideal, we know that the V plus equals the V minus. Okay? And there's no current going into the op amp. Or basically it's so small and negligible that it really doesn't matter. Okay, so what we'll do is, we could do set these equal to each other and do KCL. We'll do KCL here, and then we'll do KCL here, and then we can set them equal to each other and then find out the ratio. So the first KCL is at the at the inverting node. Okay, so it's going to be V minus V1 over R1 plus V minus V out. That's going over. That's going this direction. Okay. Over R2. That has to equal 0. The one down here, same thing. Now, this is really V plus, but it's ideal, so we'll just call it V minus 2. I mean, we don't want to introduce extra variables if you don't have to. So we'll say V minus 0 over R3. That's the one going to ground. And then it's V minus V out over R4. And that equals 0. Okay? So what we can do is solve both of these for V minus, and then find the ratio. The ratio we're looking for are these two guys right here. Those are the ones we're interested in. Okay, so for V minus, well, let's do this. Let's put this and this on the other side. So we have V1 over R1 plus V out over R2. And then if we factor out the V minus, then we have those two that's going to come and get on the denominator. Yeah, and so we don't have to carry these around. Let's just call this A. For the other one, it's very similar. So, but this one is 0, so only that one goes over there. So, V out over R4 divided by, we factor out the V minus, and so we have the 1 over R3, 1 over R4 is just going to come down here on this side. Okay, that's 4, and we'll call this B. Right? So we're going to set these equal to each other, right? And so we have our V out over R4 is 1 over B, and that's going to equal whatever that is, V1 over R1 plus V out over R2, and that's like 1 over A. We want to get the V outs together and then divide by this Vn right there. So we can have V out, and then we'll have so we're going to have these two together. So let's put this together right here. That's R4 over B minus A R2 equals V1 over R1A. Hopefully my math is right. And then so V out over Vn, I'm going to put the Vn down here, take this stuff, I'll call it C, and throw it down there. So now this be 1 over R1AC. Yeah, I'm calling this C right here. Okay. Yeah, so that's just applying KCL. Oh yeah, this is 1 over R4B minus 1 over AR2. So that's this guy right here, and when this comes in, this A is going to go on both of those, right? Yeah, so one of the A's is going to appear here, and this other A is going to appear on the R2, which is right here. That's where that came from. Yeah.
Could we leave our final answer in that form?
Yeah.
We need to
Yeah.
for everything else?
Yes. Yeah. Yeah. You guys don't have to reduce.
Oh, so it's not, we don't have to write out like all of R1, R4, and all that stuff. Like
No, that's back in algebra when you guys did all that. Yes. Yeah. Yeah. So it's like the basic steps, you know. So as long as you're clearly identifying what the C is, the A is, and the B, that's fine, you know, because one thing is that sometimes you'll make a mistake by keep carrying steps down like that, rewriting and rewriting. You might, mess up one of the, those subscripts, along the way. Even get a sign wrong. The best thing to do is group it up, call it something, and carry it forward. Anything else? I mean, I'm assuming you guys know how to reduce. I mean, that's okay, I gotta fit it on the screen. Okay, so what is V out? If V1 is 1 volt, V2 is 2 volts, V3 is 4 volts, here are those right here. Oh, what kind of op amp is this? Yep, summer, exactly. Summer in the fall. R4 is 10, RF is 2, R1 is 2, R2 is 2, and R3 is 0.5 ohms. Okay, what is this? And look, it has an R4 and R4. So that's nice. So if it has an R4 and R4, what kind of inverter is it? It's just like a unitary inverter. It's like multiplying it by -1, right? So in that case, oh, and why do you think this is there? Do you think that's like really necessary? But yeah, because this is a summer, but it's also what? It's an inverter. So here's like an inverter to invert the inverter. Okay, so so remember, here's what we know from these type of op amps that look like this, where this is RF. Here's, let's call it R1, and it has some some input right there. And here's like the output. So we know from these right here that the output is negative RF. RF is on the numerator, okay, over R1 times whatever the input is. Okay, so it's like these ratio. Now for the summer right there, we have 3 of them, right? So we have, so it's going to be like minus RF over R1 V1 minus RF over R2 V2 minus RF over R3 V3, all of that, and then it's going to be multiplied by this right here, R4 over, this R4, that type of thing, which is really -1. So really this -1 is going to make all these positive, so you're really adding everything. So all we have to do is just figure out what the ratios are and then plug in our voltages. So if RF is always 2, right? So what was R1? R1 is 2? Okay, so if R1 is 2, then this is what we have for that one. That's going to be 2 over, what's R2? It's another 2. Okay, and for this one, it's 2 over, what's R3? Oh, so that's 4. That's the only one we have to really worry about. So V1, so we have a 1, 2, and a 4. So that's, so we have a 1 plus 2 plus 16. So then the answer is like 19. Questions? You guys okay with that? Number 6. So given the following expression for gain, must be this right here, what are the maximum amplitude, the frequency, the quality factor, the bandwidth, the low frequency, and a high frequency? So so we already know this is like a bandpass filter, right? So now, fortunately, this isn't all like it's already expanded for us, which is really nice. Because if it's expanded, then it's in that form that we can recognize. And now, if I could just remember that form. So yeah, it's like omega over Q. And then S squared. You have another omega over Q. And then the last one is just omega squared. Or you could think of it like this, where this is bandwidth over S squared plus bandwidth S plus omega squared, like that. You could think of it either way, same thing. So once you have it like that, then you can just pick off your terms. Once you like massage it to the right, you force it into the right format. The problem we have is at 20. So we got to get rid of that 20 because there's nothing in front of this s right here. And then we have to worry about what we have to identify omega squared. Once we identify omega squared, then we can force this term and that term into the right shape. I mean, to the right shape to find out what Q is. Okay, so let's divide everything by 20. Divide top and bottom by 20, right? So that 10, that's going to be 1/2. And that 500, so 500 divided by 20, 25. And then 1,000 divided by 20 is like 100 divided by 2. So that's going to be 500. You guys agree with that? 50? Thanks. Okay, so now we know what omega is, right? Our omega is going to be this 5. This is going to be 5 squared. So our omega is 5, right? And so if our omega is 5, we got to force this guy right here to be 5 over something to make 1/2, right? So we can force this to be 5 over 10, right? Because then now force it to be 1/2. And so now we can say, well, that's omega's 5, and that means now we know what our Q is. Since we force it to be 5, our Q has to be 10. If our Q's 10, then we can, well, okay, so wait, before we get too far, we got to take care of this 50. So this up here, it has to be a 5. It has to be 5 over 10 too, and then also equal 50, right? So this 50 has to be equal to 5 over 10, and then it may have some factor here, A, to deal with, right? So if we solve for A, then that's going to be 500 over 5, right? And that's going to be 100. So that means we have a 100 right here, and then our numerator we have 5 over 10 s, and then we have a s squared plus 5 over 10 again s plus 5 squared. So to force it into like this kind of shape right here. Now we can just pick off what everything is. Our A, well, okay, so our A is 100. Our frequency is going to be 5 radians per second. Our Q is going to be 10. Oh, we're looking for bandwidth too. So our bandwidth is just whatever that was. So our bandwidth right here is just going to be like our 5 over 10, 1/2. And so our upper frequency, omega h, is going to be the center frequency plus half of the bandwidth. And our lower frequency is going to be that center frequency minus half the bandwidth. So it looks sort of like this right here, you know, for this like low pass filter. Sort of like that, where this is the center frequency, and then these right here. So this is like the bandwidth right here. Oh, how do we determine the bandwidth? Like if that's the maximum, what's that value right there? Yeah, 3 decibels down. Exactly. Whatever that magnitude is, this is down by a factor of square root of 2. That's the bandwidth. Unless you're dealing with power. If that's the max, then that's half of the max in power. Something like that. Okay. Questions? Okay, number 7. If the block gains of this negative feedback system are A equal 4 and beta equal 5, then what is the overall gain? Okay, so it's negative feedback, right? That gives it away, of course. Even if it didn't say it, we know it's negative feedback because whatever the feedback in is being subtracted from whatever the input is, right? Okay, and we're trying to find out the gain of the whole thing. So let's do that. Okay, so we need something like this, which is V out over V in, that type of thing. Okay, so here's what we know. From that summation symbol right here, this VD is this voltage minus this voltage, right? So VD is Vn minus Vf. And Vf, well, Vf came from this right here, passing through beta. The input of beta is what? Yeah, V out. So Vf is equal to beta times V out. And we can say that V out, well, to get to V out, the input is Vd. That's going through there. There's, something is happening, but it's being multiplied by A by 10 times it gets there. So this V out is A times Vd. So we can start plugging things in here, right? So V out is A Vd. Vn right here is Vd plus Vf, right? We're trying to get everything in terms of beta and A. So we could divide top and bottom by Vd. That'll give us A over 1 plus Vf over Vd, like that. And what else can we do? We can say, how about we do this? We can say, okay, so look, so look at this. So Vf, the numerator here, the Vf is beta via O, and Vd is right here. That's VO over VA. So we can say the VOs cancel, so it's A beta, like that. Okay. And if you guys recognize this, you may not, all the other steps, is just like derivation, but this, we've seen this many times. You might recognize this. Sometimes like sometimes you'll see this with with something else here, a T, right? Because A beta is a loop gain, T. Or you may see it where the top and bottom are multiplied. You might see it like this, just so you can put a beta there, Yeah, so if I if I pull that beta out in front, then this becomes a T, and then that becomes a T. You know. Yeah, so we've seen these two forms right there. So those might be recognizable. Okay, so for this one right here, so determine what the transfer function h must be in order to generate the following Bode diagram. It's right here. Okay, so all we have to do is, well, it starts off with this DC right here, this offset, and then we just, see how many 20 decibels, 20 decibels per decades we have to worry about going along the way. So for this first one right here, we could just say that one right there is like 20 log of 10 to the third power. Then that'll give us our 60 decibels. Because this is going to be 20 times 3 is 60, right? This piece right here, the cutoff frequency is 0.001 right there. And so that's going to be plus 20 log 1, got ahead of myself, 1 plus j omega over 0.001. That's that one right there. And that's just going up at 20 decibels per decade. So the first order. Okay. This one right here, okay, so this so it's happening at this cutoff frequency 0.01. This would continue up that way. So the first 20 decibels per decade is going to knock it down this way. And then we got to do it again to get it down at that angle right there. So it's going to be like, a double drop. So this is going to be like 20 log 1 plus j omega 0.01. But it's -2 because it's dropping down 2 slopes. You see that 20 decibels per decade slopes? What I mean is so we have that first one. It would continue off like this, but first you drop it down 20 decibels per decade once, and then we got to drop it down again, another 20 decibels per decade to end it right there. Yeah. Huh? Oh yeah. If you want to take this -2, put it right here, that's fine. Or even just take the negative and change this into a minus. You can do that too. It's fine. Yeah, whatever you want to do. Now this one right here, so this would go off like this at -20 decibels per decade, like that. But if it goes so if we do it again, it's like 1, 2, 3. It's like 3 orders more. Okay, so we're going to have like plus 20 log 1 plus j omega, and what's the cutoff? 0.1. And this right here, 1, 2, 3. It looks like we did 3 orders down, right? because if we did nothing, it would go off like this. If it went just down to here, that would just be -1. If it went down to here, because remember, this is a decade. If it went down from here to here, that would be -2 for the power, but it would, an extra one, so that's like -3 for the power, right here. And then the last one, that's a positive power. The cutoff is 1 radians per second. And so we got to go back up the other direction. So how many decibels per decade is this? This is like 40 decibels per decade. So we have to eliminate all that as we back up, 40 decibels per decade. So it's going to be 4. Okay. And then, of course, it's asking for a transfer function. I mean, it's okay to put it like this if you want to. Put your transfer function in terms of decibels. But if not, you could just take just these pieces right here, and just say, I'm just going to multiply all these things together. And take off the plus 20 log. And just multiply everything together. It's the same thing. Would have been less writing too. Any questions? Okay. Number 9. So this one says, using Blackman's theorem, what is Rn? So Rn is like right here. So what we're going to do is we're going to replace this input with the switch and do our Rn from right there. So, so what I mean by that is we're going to take this input right here, and then we're going to replace it with this switch. Right, where we're going to, when it's open, we'll look at RND. That first part right here. That part right there. And also, when it's open, this is going to be our T open circuit. And when it's closed, when we close it, it's going to be our T short circuit. And those are these other terms right here. And then we're going to throw it in here and then find out what Rn is. Looking in from that input right there. And it's not ideal. We're assuming we know this RID and, and this RO, which is really inside of here, and that's inside of there. We're assuming that those are valid. So it's like a non-ideal amplifier type of thing. Okay, so now for RIN, for RIND, that implies that you're turning off this voltage controlled voltage source right here. So that's going to be 0. So think of that as a short circuit. Okay, not an open circuit, a short circuit when the voltages are off. Okay, so what this is going to equal to, as seen from this piece right here, it looks like it's going to come down this way, right? So you have this RID, and that's going to be in series with this branch and parallel with this branch, because this goes to ground, because this is shorted. So this path goes to ground, this path goes to the ground. Right here it splits up. So these two branches are in parallel with that one in series. So let's just write it like RID in series with this R1 in parallel with R0 plus R2. Okay? That's R in D. Now for, so let's do the short circuit up here. So if it's short circuited, then this right here is just, going to ground. That's ground right here. Okay, so for this right here, we have to look at output over input. Because this is just like the loop gain for feedback. So for the feedback loop going this direction, remember this is the feedback. The input is this. VID is the input, and it goes through this piece, all these other pieces, and the output is the voltage right here. Well, the voltage right here is not 0. It is short-circuited, but it's negative VD. I'm sorry, negative VID. That's the output. So this short-circuited one right here is a negative feedback, right? It's your VID out. And that's what I'm calling, this piece right here. Divided by VID in. And so, so we have to find out what that is. So what we could do to find this right here is we can do voltage division to find this, right? So what that equals to is this resistor in parallel with this resistor. Because like, if you're at, you could pick any path, any location along here, but both of these paths go to ground, right? So it's going to be RID in parallel with R1 divided by RID in parallel with R1, and that's in series right here with these two guys right here. So that's R2 and R0. And then you're starting off with the voltage of right there, the VID, right? So this right here is what this is right there. And then you're going to divide it by this piece right here. So those go away. So this is your short circuit, your T short circuit. For your T open circuit, so now you're going to assume that this is open. And so this voltage right here is now floating, right? I guess you could think about it like that. But that also means that there's no current going through here. right? If there's no current going through here, what is VID? Yeah, it's going to be 0. That's 0. So no current going through here. So if that's the case, if that's going to be 0 for that ratio, then your VOC is 0. So all you have to do is like just, these two things and that get plugged into Blackman's theorem right there, and that's going to be your Rn. Yes?
How did you get to 0 for that? Because wouldn't you have that it's over 0 in that case?
Oh, you're talking about like this right here?
So you said the open circuit's 0, right? But if PID is 0, wouldn't that give you something over 0 for your T open circuit?
Yeah, so your denominator, you're talking about like this piece right here, right? Because that's like your input.
Well, so PID is your denominator, right?
Well, this is going to be your numerator. Yeah, so we're looking at, so we're looking at the loop portion, like the loop gain. So for the loop gain going back this direction, I know it's kind of weird thinking about it that way, but for the path going this direction, that's the input, and this right here is the output. That last branch. So that's why the numerator is going to be 0, because there's no current going through there. Okay, so
So for like an answer to that question, can we just keep it like at the variables?
huh?
So for the answer to this question, how would you want us to put it?
Oh, you mean like are you allowed to leave it like this? Yeah. Yeah. As long as the whole thing of that problem is just figuring out what these three things are. Plugging them in and writing them, rewriting them. That's because the thing is given to you, the equation. Yeah. Oh, yeah, it's kind of weird. Well, those are going to be absolute valued anyway. So that's the nice thing about it. If you get the sign wrong, you don't have to worry about it. It's really nice. But yes, I think what you're asking about, isn't this right here negative VID? Yeah, it is. So if I got the sign wrong, I'm still good. Yeah, so what will happen is like you'll have like another negative in there that cancels out with that negative, then you end up with a positive, but then you'll take the absolute value. Okay, so what is the power being delivered to RL? Assume R0 within the non-ideal amplifier is 0 ohms. Okay, so we're looking for, okay, so if it's RL, we're looking for this voltage right here, and then we know the power through that is just that voltage squared divided by RL. Can you guys see the green okay? I know the black was kind of running out. You see the green okay? Okay, so basically this is a problem of just trying to find out what this V out is, right? So we could just do KCL right there. So first let's do the easiest one, the current going down this direction. So that's going to be V out minus 0 over RL. Now the current going this direction, okay, so that's VID. What's the voltage right here going to be? Yeah, A VID, exactly. So there's no current going through here, so the voltage drop across this resistor is going to be 0. So I'm going to start off with 0. I'm going to go downhill some Vx, downhill 0, there's no voltage drop. But then I'm going to go uphill some AVID. So that's what the voltage is right here. It's all those added together. I mean, you're starting at 0, and then you're climbing up to find out the voltage on both sides of that resistor. So you're going to have V0 minus all this other stuff. So you're going downhill Vx. That's 0 across the resistor. But then you go some uphill, some A VID. All over R, R5. Okay, and the last current is going down this direction right here. Okay, but I mean the current across here. So it's VO right here. Right here is, well, you got to find out where it came from. So this voltage right here is whatever this is plus some Vy. That voltage right here is like this minus VID going from here to here. And that voltage right here is this minus Vx. So it's V minus on one side, and the other side is this minus Vx minus VID, and then plus Vy over R2. And that has to sum to 0. You guys agree with me with that? Okay, so once you have this right here, you're able to easily solve for VO, right? And then your power is just going to be VO squared over RL. Okay? But of course, for the KCL, the tricky part is, what's on the other side of that resistor, what that voltage is. Okay, good. 2 more left. Oh, do you guys have any questions on this one? Before you? Huh? Oh, well, you have to solve for power. It's like, yeah. So this equation solves for VO, because the only unknown in this equation is VO. Yeah. And then that gets plugged into that, and that's power. So 2 equations, 2 unknowns. That's all you need. Okay, so for this equation right here, this problem right here, what is VO in terms of VI, R1, R2, R3, A, and C, if C is the common mode rejection ratio? So you have a system like this, and this VDM is the voltage across here. Excuse me. Okay, so we want this V out, and we know the V out is going to be like this when we're dealing with this the common mode rejection ratio. It's going to be this. We know whatever is like at the input, and that's that VDM plus this VIC common mode input over your CMRR, or what we just called it C. Okay, same thing. Okay. So, we're given this. We just need to find out what this is and what that is. Okay, so this VDM is just the V plus minus V minus is like here to here. So we got to find that voltage and then that voltage. We could do both these voltages by voltage division, because no current is going that direction. Okay? So V plus minus V minus. And V plus is equal to, for voltage division, what's below is R2, R3. On top is everything. And it starts off at VI. And V minus is, on the bottom of that, is just R3 over all the resistances. Starting off at VI. So that's that. For this one right here, the VIC, that's, that's V plus V minus, because you're just doing average there over 2. And we found out what each one of those are. Okay, questions? So remember, this common mode input is just the average, and this is the difference. This is like the ID. You know, when it says VID, same thing. It's just a difference between those two, whatever across those. You guys good? Yes. Oh, that's the common mode rejection ratio. That's this piece right here. Yeah, so typically, you know, you want that to be like a really good value, so this piece right here becomes insignificant. That's the goal. So you want this to be like quite a large value.
Or that's not something we solve for.
Oh no, you assume it's given to you. Yeah. So like when it says, like, you know, what is that in terms of all these things? Basically, you're just assuming that all these values right here are given to you. Yeah, like they're numbers, actual numbers. Oh, this right here? This is VIC equal V plus V minus quantity over 2. So it's the average of these two guys going in there. That's the common mode input. I know you would think it's CI, but in the book they say IC, or common mode input. So if an amplifier's gain can be described by a single pole low pass characteristic, then what are the values for the cutoff frequency, bandwidth, maximum amplitude, and unity gain? So here's like this single pole low pass characteristic right here, and we're trying to find out all these things right there. Okay, so for that, okay, so we have this A that equals 0.8 meg over S plus 10K. And we know the form, we recognize this form right here. Right? Single pole, low pass. That's what that is right there. Okay. So, I mean, if we were to plot this out, low pass is like this, where this right here will be omega B, this right here would be A, this right here would be omega T. That, you know, the unity gain. The slope, you already know what's the slope? What's the slope of that? Yep, negative 20 decibels per decade. Because it's first order slope. Yeah, that's low pass. So so we have to find the cutoff frequency. Well, we know the cutoff frequency, right? So omega B is going to be 10K. What's the next thing? Cutoff frequency, bandwidth. What's the bandwidth? Good. Yeah. Yeah, omega b. Yeah, so yeah, so he said -0 because, you could have a system like, where it doesn't all go to 0. Like our, you could have a system like this, where then it's like that omega minus that omega. What about omega t? That's the unity gain frequency. What's that? That's the frequency that makes this 1 or 0 decibels. Same thing. That's just this right here, this whole numerator. So whatever this is. So in this case, it's going to be this right here. Is that it? Oh, maximum amplitude. So what's the maximum amplitude here? Yeah, so in that case, okay, so this right here is, okay, so our A omega B is this whole thing right here. So A is going to be this divided by our 10K. And you can leave it like that. Okay, you have to like yeah, you don't need your calculator. I mean, you could use it, but you don't really need it unless you just like if you want to verify something, sometimes it's good to like plug something in to see if something is equal to something else or whatever. But yeah, you wouldn't need your calculator. Any questions with this problem right there? Okay, looks like we're good. All right. All right, well, good. Thanks for coming today on this Sunday. School on Sunday. Where are we coming to? All right, see you guys tomorrow. Hey.
What did you say? Why was that one 0?
Oh, yeah, because this piece right here is low pass, so low pass goes all the way over.
Okay.
Now, if it was high pass, that's the opposite, right? If we had a high pass one that went like this, then this has infinite bandwidth, right? Because you got infinity way out here, and then you got this omega h right there. So, it's like infinity minus h is the bandwidth. So high pass are infinite bandwidth, but low pass just go to 0. Exactly. Yep. Mm-hmm. Hey.
Quickly explain how this would change, like why it's -0. I know you explained it, but I sort of didn't understand.
Oh yeah. We were just talking about that. Yeah. So the reason why is because you're trying to find out what is the bandwidth of all the frequencies that could pass through. So there's a range of that. The highest is omega b, but the lowest is 0 frequency. So that's the entire range. So it's like the high minus the low.
Okay, so it's the full range.
Yeah, the full range, and then for high pass, it's infinite because the high is infinity and the low is this, so it'll be infinity. But typically, when you want to think about it like that, is like when you have like a mid-range bandwidth, where that's the high and that's the low, and then that's when you have like a non-zero, left-hand side. Yeah.
Okay, thank you.
All right, cool. Yes.
I think I was just confused about just like how that became this.
Wait, which one?
So that one right there.
Oh, yeah. Okay, I skipped some steps. Sorry about that. Yeah. So, okay, so if I remember correctly, we had A over 1 plus AB, A beta. Okay, so what I did is I multiplied the top and the bottom by beta. So I didn't change a thing. I multiplied it by 1. This beta I pulled inside and I kept that one outside. So it ended up being like this. Right? And then both the A betas became T because that's what the loop gain is, like that. Yeah, so whenever you see your A and your beta together, that's the loop gain right here.
T is the loop.
Yeah, T's the loop gain. And because your signal is going through A and then it's coming back around and going through beta, that whole thing right there is what is called loop gain for both of them. Yeah. Yeah, that's right. All right, cool. Mm-hmm.